Hey, come on in, get settled. We'll start in about 30 seconds. Okay, I'd like to get started. Welcome back. There are more empty seats today. That's good. I don't recognize that in the system because I'll say this later in the enrollment. I only had 12 people who dropped so far in the system. So those of you waiting to get in, right now it looks very promising. So that's good. I want to start with a few announcements. Just a reminder about class use of technology. Refrain from it if you possibly can. Try not to play on Facebook for the entire class. Come pay attention. If you are taking notes, that's fine. I probably don't believe you, but that's fine. So try to refrain from that as much as you possibly can. Read Norman's book, please. It's an easy read. It's a fun read. So I hope you actually enjoy reading that book. Definitely have to have it done by the midterm because I'll test you on some high-level parts of the book. But I will do a lecture on principles of design, so certainly by that time, I think sometime in the next week or two. But over the Labor Day weekend, I think you could probably get the book read. The pitches and introductions, which is part of homework 1, should be posted by class next Tuesday. All the assignments in the class are due by lecture time, so 9:30 in the morning. And in fact, the links are set such that they disappear at 9:30, so you have to get them in. Okay? Otherwise, you won't be able to turn it in. There has been a very nice beehive of activity. So there's been about 70-some posts. Almost 50 people have done it. I'm expecting another 50, if not 100 people to actually jump in. So there is a lot of activity. If you haven't yet looked at that, you're sort of missing out. So do post, do introduce yourself, do discuss project ideas. And I've been sort of browsing through there. The teaching assistants have been as well. And every so often, if I have something to say, I'll reply to your comment about a project or for some of you to tell you that your videos were fantastic. So thank you. To help us out in Compass, Compass has a couple of quirks in it. One is that if I don't assign it as an assignment, I can't give you a score in the gradebook without a whole bunch of labor on my end. So when you are done with the assignment, on that first in Compass, in the schedule, on the first link, go into that lecture, and there's an assignment for homework 1. Okay? Click into it, and actually submit just done, I did it, my post is there, whatever you want, and click submit. What that does is it shows us that you actually did the work, and then it's really easy for me to go in and give you a score. Okay. Browse the posts, make contact, and start forming groups. Jordan, you have a question? So his comment is, rather than only put your name as the kind of the subject that you see on the main screen, is to maybe put your project idea. Makes it a lot easier to come back and revisit that idea later on. Okay, so thank you. That's a good suggestion. So I want everybody to be in a group by September 9th. Sounds like another month, but it's really not that far away. It's the week after next. And then we're going to work really hard right after the 9th for students who are not yet in a group to get you in a group, either by extending the groups that currently exist who might want additional team members, or by taking you and forming new groups altogether. And what I'm going to do next week, I haven't yet put this in the course schedule, but what I'm going to do is I'm going to push everything down and make room for one lecture to discuss projects. I've already put together a draft, and I have a tour of prior projects that students have done. I think that would be helpful to you. And also to talk about just group work in general, both the benefits and tips for working in groups. And thanks to one of the teaching assistants, it pointed out to me that, we ask students to work in groups all the time, but we don't really tell them how to do it. I'm like, yeah, that's right. We don't really tell them how to do it. So what do we have to say based upon 12 years of experience and looking at some other resources? So we're putting together a lecture for that, and we'll deliver that next week. The enrollment update, as I had mentioned, wow, there's a lot of empty seats. So that's good. I guess I scared everybody away. Now's the time I say, oh, all that work I said is not really true. It is. There's been 12 drops, according to the system, since Monday. Looking at empty seats, I think there's probably going to be more. So those of you waiting to get in, it looks very promising. However, before you actually are able to register, please do not join a group. If you join a group and you influence the group, like you choose the project and the group rallies around it, and like, oh, by the way, I'm not going to be here next week or the rest of the semester, that's probably not good. So we'll help you. If you get into the course, we will help you get into a group. Okay? So just be patient. If you're not yet in the course and you want to be by next Thursday, come talk to me next Thursday, and we'll see where we're at in terms of seating and so forth. And maybe I can get you in. Because if there's lots of empty seats, my assumption is that people have dropped. They just haven't done it in the system yet. Okay, so let's recap from last time. We had a definition of an interface, and we talked about that definition being sort of, we have many, but the one I gave you was sort of the simplest one I could think of. It's the translation from goals, or the mapping of the user's goals, onto system behavior. And it already opens up a lot of interesting challenges about UI design. Whose goals are we talking about? Which ones are they? What is the correct mapping, and how do we know that it's useful? That led me to talk about 3 different challenges. Of course, there are many, but I emphasize 3: understanding, mapping, and evaluating. Understanding was just understanding behavior, what drives people. And the interesting thing about behavior is that it's highly individualistic, and it's very contextualized. And what that means is that in almost every different context in which interfaces are used, there's going to be different motivations, there's different behaviors. We have to understand that because it's going to lead to a different design. Okay? So that's why we have a lot of different techniques for doing user research: interviews, surveys, contextual inquiries, and so forth. We're going to learn about some of those techniques. The second challenge I talked about was mapping. And mapping is just basically getting your ideas onto paper for what that interface is going to look like. Mapping is hard because you have an infinite number of possibilities. Think about all the different icons and colors and layouts and actions and so forth. You can have any combination that you want. So the design space is essentially infinite. So we need techniques to help us. One is we want to have good user research results, so we have a good starting point. And second is we need techniques to do rapid experimentation so we can navigate that land space quickly and iterate on our ideas. And we'll talk about that with low-fidelity prototyping, heuristic evaluation, cognitive walkthroughs, and so forth. And the final challenge I mentioned was just evaluation. And the interesting thing about evaluation is nobody ever does what you expect. It's a little bit, it can be frustrating, but it's also fun, and it's eye-opening. And I had mentioned that every study that I've ever done in the past 12 years, even though I think I have a very clear hypothesis about the way people will behave, they always surprise me. And that's one of the interesting things about evaluations. Behavior is very unpredictable. And what we want in the end is we want interfaces that produce a distinct and desirable experience, and that's often called a value proposition. Okay, so you're willing to purchase this interface, and in return, this is what I hope to deliver to you. And that's the story. Okay, that's the story. That's a big part of interface design. Okay, today, we're going to go back in time. And we're going to rewind to the birth of personal computing. Now, depending on how you want to define personal computing, we can date this event to early to mid-1970s or as late as the early 1980s. And I'm going to go with the year 1981, because that was the time at which the first commercially available desktop computer, the Xerox Star, which is shown here, was released. Now, 1981 was a really long time ago. In fact, many of you probably weren't even born in 1981. So I was worried that 1981 is too foreign. So let's try to contextualize what 1981 was like. In 1981, that guy, Ronald Reagan, was the president of the US. In 1981, the top Billboard chart on the year was Bette Davis' Eyes by Kim Carnes. I was going to play it, but thought probably not. In 1981, the Rubik's Cube was still, oh, so cool. I had that book. In 1981, Illinois football had a winning season. We were 7-4 overall that year. In part, I picked 81 because that was like the only year I could find that we actually had a winning season. And only in my notes, I was 10 years old. That is not in your notes, only mine. Okay, so 1981, the interface was new. The vision was that everyone would own a personal computer. But the landscape of applications and interaction design was vast and unknown. You could have anything you wanted. You could have any color. You could have any icon. You could have any interaction. You could have any layout. Which one was good? And how do you know? I mean, even at that time, we were thinking about what does it mean to have good design? If you have two or more alternatives, which one you would choose and why? And what's the right kind of data to collect to make that decision? It turns out that developers were already grappling with those types of tough choices between design alternatives in terms of layout, colors, icons, response times, and so forth. And the problem was that there was no body of knowledge. I mean, who do you turn to? What resource do you turn to at the time to help you make those types of decisions? Well, there were a few pioneers in the field, Stuart Card, Tom Moran, and Alan Newell, who sort of, the epicenter was Xerox PARC at the time, recognized that problem and believed that psychology already had many of the answers that people were looking for. There's already a large body of knowledge in regards to perception, memory, problem solving that was developed as part of what's called human factors, which is sort of an offshoot of psychology that dates back to World War II. There's always a lot of sort of confusion about what's human factors, what's HCI. Here's a very simple thing for you to think about the difference. Human factors that really emphasizes the H. HCI really emphasizes the C and the I. Okay? There you go. But there was a really big problem. Computer scientists who were building the interfaces were not that familiar with the literature, and frankly, they didn't really care. The data was scattered across many different publications. It used esoteric languages. And it was sort of hard to figure out because you have one study that says one thing and another study that explains it away. So what the three pioneers thought was they wanted to aggregate that knowledge in a form that would be easily accessible to computer scientists into what they called an engineering model. Okay? And that was reflected in a very famous book. It's unfortunately out of print nowadays, but it had a huge impact on the field. And in that book, they painted a very bold vision. And the vision was to be able to model the human and predict behavior. To make that model, we needed really descriptions of three things. We needed descriptions of the human, descriptions of the task, descriptions of the interface. And what you would do is once you had those descriptions, you would use them as input in sort of this magical system that we call the computational cognitive architecture. And it would spit out things like response times, error rates, learn times, and so forth. And by flipping different switches, I could say, okay, well, we could have, say, a female, 18 years old with 20/20 vision versus an elderly male with less than normal vision. And you would put it in the system, and you would immediately get a response about the differences in performance, learnability, error rates, and so forth. It's sort of magical to make that happen. But if you could achieve that, wow, that would be fantastic. So you could do experimentation without ever having to do a user study. User studies, well, they were, and they are expensive. You have to recruit people, bring them in, have the procedure, collect the data, analyze it, figure out what it says, and then repeat every time that you make a design iteration. Well, here we just flip some switches, push a button, and we get the response. That would be amazing. Okay? This vision called into action lots of different academics and industrial research labs who worked toward this. People worked on task description languages. They worked on interface description languages. People still work on computational cognitive architectures. What Card, Moran, and Newell worked on was that model of the human. That's why I have it in red. So this seems somewhat fantastical. And arguably, if we look forward to today, it's questionable how successful this was. Okay? That's not the point. The point is it had a big impact on the field. And second is I think this is also interesting because how do you move a field forward? You almost always have to have a compelling, bold, forward-looking vision. And that's what they had. And lots of people came together to help push that vision into a reality. In fact, this is a microcosm of how US science policy operates. You have some of the smartest people in the world who come together, and they think about strategic initiatives for science in the US. It goes through a bunch of different hoops, and pretty soon it gets tens or hundreds of millions of dollars attached to each of those initiatives, and then people bid for that through a proposal process, get the money, and they work on solutions to those very hard problems. Okay? So their model of the human was called the Model Human Processor. It looks something like this on the right. I took a little bit of liberty. This is my interpretation of the Model Human Processor, but it very closely reflects what they had in their book that was published in the early 80s. What's interesting about the Model Human Processor is that it's a human analog of a microprocessor. And it reflected a broader movement in psychology at the time to think about people as information processors. The dominant theory at the time was what's called the SR model, stimulus response. It sort of treated behavior as an invariable black box. Give you a stimulus, and you respond the same way. Had a hard time differentiating why you would have different behaviors for the same stimulus, but in different contexts. Information processing looked at people as, well, information processors, but your behavior is a function of prior experience and the task environment and the context. So let's just go over what's in the model. It has three interacting subsystems. It has the perceptual system, has the cognitive system, and it has the motor system. So the perceptual system transforms the raw sensory stimuli, what I see, what I feel, what I hear, and so forth, into an initial set of symbols that gets passed on through the sensory stores, through working memory, to the cognitive system. The cognitive system further processes that information and creates and stores and retrieves what we call associations. And I'll talk about that in memory. And if action is required, it activates the necessary memories, passes that to the motor system, and that gives us, our hand, wrist, and arm movements. It operates in an infinite loop. It typically operates in a serial fashion, but it can do it in parallel for highly learned tasks. So it mimics microprocessors in the sense that it has a fetch, decode, and execute cycle. So the fetch is the perceptual system. It brings in the next sensory stimuli. Decoding is through the cognitive system. And the execution is through the motor system. Every system has its own memory and its own processor, and we'll talk about that. Memories have a capacity and a decay time, and processors have what we call a cycle time. Every system has known properties. It's guided by certain principles of operations, and we'll talk about those as well. But if you look at this, this is very abstract, right? It's highly unlikely that this is an accurate depiction of our cognitive system. Highly unlikely. But it's a model. It's an abstraction. And the model is useful for forming hypotheses, reasoning about why things occur, and conducting experiments. Okay, and perhaps that was the biggest impact that this system had. There's a few notable things that's not in the model. One is haptic processing and memory, so your sense of touch. Kinesthetic, or the motor memories. So it started remembering where things are at and how to perform certain actions. And it also doesn't have what's called attention. So attention is sort of like a bucket of resources that's bounded that you have available to you. A large chunk of that is allocated subconsciously, but part of it you can direct consciously. That's called selective attention. The example that gets used often is that cocktail party effect. So you hear a lot of ambient noise, but somebody says your name and you're tuning in on that. Or perhaps in the visual field, there's something that's happening that you sort of focus on at the expense of other things. That's selective attention. And then you have capacity. This is the number of things that you can attend to at once. It's hard, actually, to attend to multiple things in the same modality at once, but we can attend to multiple things as long as they're in different modalities at once. So basically, driving while you're listening to music tends to be OK. So let's start with the perceptual system. Like I mentioned, this processes the sensory stimuli into higher order symbols called chunks. And it involves recognition, organization, and interpretation of the stimuli. It's an amazing and complex process that's not fully understood, though we do know quite a bit about it. And it exhibits certain properties, such as what we'll call constancy and abstraction. Constancy is just that I recognize things to be the same, despite differences in illumination, distances, orientations, and so forth. In abstractions, I take different symbols of lines and shapes, and I can sort of make sense out of them at a higher level. So if you look at this image, if you haven't seen this before, it probably just looks like a lot of white and black blobs. But if I told you there's a man's face with a beard in the upper middle, usually that makes people see it. It creates what's called an expectancy effect. Okay? It activates that template in memory that hints the perceptual system how you organize that information. But perhaps what's most fascinating about that image and having you see the bearded man's face in it is that once you see it, you really can't unsee it. And that, to me, is a microcosm of user interface design. Once you create something and you spend all the time in the kind of the studio room working out sketches, doing the user research, doing the user tests, and so forth, it's really hard for you to unsee it, and it's hard to imagine how somebody who wasn't involved in all of those design discussions, how they probably can't see it in the same way that you see it. It's the same thing. Once you see something, and once you're deeply engaged with it, it's just really hard to unsee it. According to the model human processor, perception is both discrete and it's limited. By discrete, what that means, it operates not continuously, but it operates in cycles. So on every cycle, I basically fetch something from the sensory, or from the task environment, and I do some processing on that. The problem is that the amount of information that's there is far greater than the time I have to analyze it. And so it's limited. You have to be selective. You have to prioritize what you're going to process and what essentially you're going to throw away. So that process is driven in part by selective attention. So you're going to force yourself to look at certain things, say in the visual field, or things that you're trying to listen to, and by prior experiences. And the cycle time is estimated to be about 100 milliseconds, though there's a lot of individual differences. And those times just from, say, young to old can vary quite greatly. You get this effect with the cycle times called perceptual fusion. And essentially what that means is that two things that come within one cycle time tend to get fused together. So this is the reason why we perceive animation as being smooth if it's greater than 10 frames per second. That means you get two different pieces of information that come into the system within that one cycle time. Your responses feel instantaneous if they're less than one cycle time, about 100 milliseconds. And that causality, cause and effect, is strongly influenced by that notion of fusion. There are two different theories about how we have perception, how it works. One is what's called a top-down or constructivist theory. The other is bottom-up or ecological theory. Top-down argues that it's driven a lot by experience, by expectation, and by knowledge. And essentially, it's pattern matching. It's templates. And the way it often gets explained is through kind of these dual images. And so I can sort of direct which one you see by just giving you a statement. It creates the expectancy effect. And so, start from your angle. The one on the left, I told you there's two faces. You should sort of see them. If I told you there's a vase in the middle, hopefully you see that. The next one, if I told you that it's a man playing a saxophone, you see that. If I tell you that it's a woman's face, you see that. And so I'm creating that expectancy effect. It's top down. Perhaps you don't see it until I say what to look for. The one on the right, it's either a white angel or a 4-point setting that's holding a ball. Okay? But it struggles to explain other things. So it struggles to explain how we make sense out of environments that are foreign to the mind. And that's where bottom-up or ecological theories come into play. But this just assumes that all the information required for perception resides in the environment itself. So the process of information begins at the level of the neural signals, and it passes through a series of processing stages that assign higher order meanings. And so an example of bottom-up processing is sort of this digital representation of speed in a car. And so every time that you glance at the display, it takes the same amount of time to determine how fast you're going, no matter how many times that you looked at that display in the past. And so memory in these cases serves little to no role in that situation. And bottom-up processing really doesn't require any type of higher order thought. So if you compare that like digital display to an analog display, there's very clear differences. With an analog display, for instance, you sort of know in your car where that needle needs to be and what that tells you in terms of how fast you're going, but it's less precise. Right? So, but you can glance at it and get a sense of how fast you're going because it matches that template, whereas here it always takes the same amount of response times. Okay, there's also one more. It wasn't necessarily in the model human processors, but it's something that we see a lot being leveraged for UI design, and that's called Gestalt theory. And so I want to talk a little bit about Gestalt theory. The other theories of perception assume the existence of what we call part-whole hierarchies. That's the environment is composed of elementary units such as shapes, lines, and colors, and so forth. And those units have to be organized to derive higher order meaning. Gestalt argues that the concept is actually inverted. It argues that we perceive the whole first, and then are able to decompose it into elementary units. And Gestalt theory argues that organization is a fundamental building block of perception. These laws are directly applicable to UI design. So let's go through several of them, look at some examples. So the first one is just the law of proximity. It's a very simple law. Basically, things that are spaced together go together. So things that are proximal get perceived as groups. And so here, just the login for Facebook, at least when I took the snapshot, is you tend to see 3 groups. I think I can actually write on this. We perceive 3 groups, yeah. Perceive this one as a group, this is a group, and this is a group. And it has a very kind of minute difference, right? It's just that the spacing between here is less than the spacing between here, okay? And the small difference in how negative space, or the background, is utilized helps us see things in different groups. Here's one from a second one that shows the law of proximity from Kickstarter. And it's immediately obvious which pieces of information go together and which ones relate to different projects. And though they do have a very kind of fine border, it really is unnecessary, because you would still perceive that with or without the border as being in different groups. And that type of a grid layout is very common in UI design. Another law is called the law of similarity. Basically, things that look similar go together. And so Windows Explorer uses this so that when you do a selection, the operating system renders these things in a similar color, and it creates an immediate grouping that pops out relative to other things in the background. Another use of the law of similarity, Zillow uses this in their visualization of things versus for sale or versus for rent. So you immediately see the different groupings based upon the color. Purple being sale, red being for rent. You also have what I call the inverse law of similarity, that things that are different pop out. And so if you look at that image, you sort of can't help, but your eye kind of goes down to the Sign Up Now button. And you see this used a lot in web designs, where you have the join button, the kind of the key action button, the donate button is in a different color that stands out. Maybe it's a different size, larger font, but it stands out from what's around it. And you sort of can't help, but your eye kind of navigates that and sees it. So things that are different will stand out. We have what's called the law of closure that states that we perceptually close or complete objects that are not, in fact, complete. And it's used a lot in logo design, so it's used in the IBM logo. The I, the B, the M aren't fully complete, but you perceive it to be. It's also used in I think this is the World Wildlife Fund logo as well. We have the law of figure ground. This law basically argues that we divide the visual scene into a foreground and a background. And the Mac logo uses that to create a very interesting visual effect. It's either a profile of a happy person looking at a computer screen, or the computer screen with a happy face on it. But the idea is that it's difficult or impossible to focus on both of those interpretations at the same time. And we have the law of continuity. This just states that the objects that are perceived along a continuous path are going to be perceived as a group. And so here the watches in the upper left follow the same arc of a circle, and so you perceive them as a group. And we perceive objects that are discontinuous as being in different groups. We also have what's called pre-attentive processing. This is just the rapid detection of certain signals. It circumvents focused thought. And so we have certain signals that just pop out, and it just goes around the normal kind of processing that we have. And we use that a lot for the design of visualizations. So things like in the upper left, if I said find the circle, you can do that quickly. So shape is a pre-attentive processing unit. If I said find the red circle in the second one, you can typically do that very quickly. You don't really have to even think about it. It just sort of appears. So color is also one. Orientation in the top right. If I found the one that wasn't perfectly horizontal, again, you can pre-attentively process that. And so orientation is also an attribute. In the lower left, find the one that's longer. So length is a pre-attentive attribute. In the bottom middle, if I said to find the one that has a different saturation or value, you can tend to do that very quickly. That's also a pre-attentive attribute. And in the lower right, find the one that has the shadow. Again, you can do that pre-attentively, so you don't really have to think about it. It just happens fast. And there are more. Okay, but people who are very good at visualization design will use that. And so this is an example where if you had something that you wanted to pop out, I mean, you just cannot not see the large orange circle in that visualization. It just pops out, and so you can't undo it. Okay, perceptual memories. This is just the manipulation and the temporary storage of visual and spatial memory. And the current thinking is we have sort of two different stores. We have what's called the visual spatial sketchpad. And so if you're driving and you're making sense out of the visual scene, that's using that sketchpad. It has a 200 millisecond decay time. And we have what's called the phonological loop. Stores linguistic information, so processing language, text in a book, my voice in the lecture, and so forth, and it has a 1500 millisecond decay time. And you can sort of hear that phonological loop. It's actually called the articulatory loop. If you can listen to yourself speak, or you sort of don't say anything but you just talk to yourself, that's the articulatory loop. Each can be used simultaneously. So generally speaking, listening to music that has lyrics is more distracting when you're trying to focus and write than it is, for example, when you're driving. And the reason is that it's actually using two different sensory stores. One of the guiding principles is notice that where we have a variable, what's called a variable processor rate. And what it says is that the greater the intensity, the lower the processing time. And so a couple of examples of this. If you have a brighter screen, it tends to need a faster refresh rate. Maybe a more familiar example to you is that you perform better when you're under pressure. So when you take the exam in the class or exam from any other class, there's a lot of stimulus intensity, okay? Cycle time decreases. You have to use more energy to have that lower cycle time, and you feel somewhat exhausted after the exam. Do you feel like that after the exam? Yes. You also remember all the things that you couldn't remember after the exam. Okay, and then we have another thing called encoding specificity principle. This just means that memory is better when the context available at the time of encoding is also available at the time of retrieval. So things like location or place, the time of day, the mood that you're in, sounds that were co-occurring around you are all different types of retrieval cues. But we might forget because we have either too few cues, and so you don't really know where to start, or they're ineffective, so it takes you down the wrong path in memory. It's actually that concept has inspired a lot of different kind of interesting research. And so I could pick many examples. This is just one I thought would be interesting to talk about. It's recent. This inspired what we call context-based search. So for example, this is the Refiner system. You can search local information based upon the time that it was stored, though that probably isn't so novel. But you can also search it based upon the location at which you access it. So can't remember the name of the document, but I remember I had it open when I was at the coffee shop. I could do that type of search. I could also search based on things that were co-occurring. It's like, again, I can't remember the name of the thing that I was working on, but boy, I was listening to this particular song by an artist at the time. I remember that, and I was at the coffee shop. So you can search your hard drive based upon those types of cues. Okay, we'll move on to talk about the cognitive system. Does the bulk of the work. Solves problems, makes decisions, allocates resources, and it schedules motor actions. The first thing we'll talk about is long-term memory. It holds the mass of knowledge. We have different types of memories. We have what's called semantic memory. These are the facts, the concepts, procedures, and skills that I know. But I also have something called episodic memory. This is the order of events and experiences in time. So semantic memory example would be something like, oh, how do I set styles in Microsoft Word would be one example. An episodic thing would be, what kind of code did I write last week? So that was more a time-based retrieval. It's thought to have infinite capacity. Yet it's fast read and slow write. That means you can get things out of memory quickly, but it's hard to get things into it. But once you do, it basically is infinite capacity. We talk about what's called elaborative rehearsal. I'm sure you heard this, but the way that you remember things isn't just rote memorization. I suppose that can work, but it's actually better if you think about something more deeply and you try to relate it or associate it with other things that you know. And if you do that, you have a better chance of remembering it because it creates more retrieval cues for you. One particular model of long-term memory commonly used today is that we have association-based memory. We have many individual units. It could be a letter, a number, symbol, so forth, that's stored in a neuron and that linked by associations. And associations play sort of multiple roles, but they help to form concepts, helps to form what we call is-a-hierarchies, and to relate different concepts that we have. So it's sort of similar to what we think of when we think of a semantic network. That notion of infinite capacity with long-term memory is nicely explained by this particular model, because what it argues is that it's the pattern of activation that represents meaning, as opposed to any one specific, say, neuron. Okay, so if you have, say, 8 neurons, and it can be on or off, how many different alternatives can you have? Well, 256, just like when you have bits. Okay, but what if I had tens of millions or hundreds of millions of neurons? Now you have 2 to that. And so that's how you get this notion of having infinite capacity. We think of it as being partially distributed. So a neuron participates in the storage of many items, and an item can be stored across many neurons. Thought. Well, it's thought to be the spread of activation. So your current thought will activate one pattern, and that creates kind of a chain reaction that activates the next pattern, the next pattern, the next pattern, and so forth. And that chain of activation can be influenced by 3 things. First, the location. Second is the strength of association that you have between concepts. And third, the radius of activation. And it's thought that people who have larger radii of activation are more creative than people who have a very narrow radius of activation. So this is one way that people test your radius of activation. So let's just do this for fun. Okay, so what we got to do is I give you 3 words, and you have to think of the word that unifies them. And the theory is that those people who have a larger radius of activation can actually do that more easily than people who have a more narrow radius of activation. So if I said broken, clear, and I, shout out the response. Who said that first? Put this man in your group. Plain, credit, report. Card, yeah, there's another person who should be in somebody's group right away. This is hard. Sore, shoulder, sweat. I haven't heard it. There might be multiple answers, but there's one that I know. I still haven't heard it. Probably not. Cold. Oh, I know. I've done this one before, so I know. I probably couldn't have gotten either. That's okay. But that's the idea. Okay? And sort of that theory is interesting because there's a lot of theories of creativity and group work that get built around this. The fact that you want groups who have people with different life experiences because they have different associations, you start in different locations, and you just think differently. And even in brainstorming, if I say an idea, that sort of activates a certain memory in your brain. And that activation might lead to different associations, and you say something that activates something in my brain that leads to different associations. And so it's that back and forth and building off of each other's ideas, that stimulation that you have in memory of different locations that you by yourself wouldn't have been able to activate is what underlies a lot of kind of group work and group brainstorming and so forth. Okay, working memory. This holds intermediate products of thought. It's thought to be very small. It holds what we call 7 plus or minus 2 chunks. It's a terrible word, chunk. But I don't really know why they chose the word chunk, other than the fact that memories can be at different levels of granularity. It can be sort of things that are very small, like a digit, but we can also think of like somebody's phone number. And so to capture that different level of granularity, they just came up with a sort of abstract, general use term called a chunk. And Miller had a very famous paper, I think it was back in the 1950s. It was called the magical number 7 plus or minus 2, and that's what we think about today. We think that we have 7 plus or minus 2 chunks active at any given time. It used to be that we thought that we had a separate area for working memory. Now it's thought that working memory isn't really a separate area of the brain. It's actually all the same part of memory. It's more like, how would I describe? If you took an aerial photo of a city at night and you saw lights flashing at different locations in that city, that's sort of what working memory looks like. And they've done fMRI studies where it can take scans of your brain in real time as you're thinking about things. That's sort of what it looks like. And so there isn't really a separate space. It's really part of long-term memory. It's just that you have a certain things that can be activated at once. It's small capacity, but very rapid access. We have what's called the discrimination principle. That just means that recall is determined by the candidates that exist in long-term memory relative to the cues. Well, we could have too many candidates, and that might give you a false memory. But you can also have too few or ineffective cues, and you wouldn't be able to recall things. And that would be a retroactive memory lapse. But we can also have what we call prospective memory and lapses. This is about things that you have to do in the future. So, boy, I know I have to go. I have to finish homework 1 by next Monday. That's something you have to do in the future. That is time-based. You also have what we call event-based prospective memory. So, I have a message from my roommate, and the next time I see that person, I need to remember to tell them that so-and-so called. Okay, that's an event-based prospective memory. And the time-based ones are much harder to remember because there isn't really like a cue that activates them. Okay, so the next time you miss your doctor's appointment, just explain to them that research shows that it's a much harder thing to remember than the event-based. Probably won't work. We have what's called proactive also and retroactive interference that can cause memory lapses. It's hard for me to remember these things, but let me try to help you the way I do it. So I think of proactive as going from the early, and I just draw an arrow to the current. Retroactive from the current, and draw an arrow to the previous. That's how I sort of remember it. So proactive is that I have a friend, they got a new number, and I'm trying to recall that new number, but I can only think of the old one. So the old one is interfering with the new one. And vice versa with retroactive. So I go from the current to the old in terms of my interference. So retroactive, you want to recall the old, but you can only retrieve the new. Okay? So the new one's interfering with the old one. That's retroactive. There's a number of cognitive principles. One is called the uncertainty principle. This just means that decision time increases with the level of uncertainty. That's called entropy. I have part of a lecture coming up on Hicks' law, and that deals with the uncertainty principle. We have the variable rate principle. That just means that the cycle time is shorter for increased task demands. Again, that comes back to when you take an exam, you sort of feel exhausted after the exam. At least I always did when I was a student, for exactly this reason. It takes more energy to run your system at a higher rate of speed. And the last one is called the power law of practice. It's a really simple idea. Basically, you get better at things the more that you practice it. And there's a constant that goes with this. It's usually about 0.5, though it can vary from 0 to 1. But this is really important when you do HCI experiments if we're really concerned about response times. And the graphs almost always look like, if I can write here, just kind of small. Looks like this. And this is on the x-axis, we have the number of trials, which is n. And this here is my response, how quickly I can do something. Okay? And the graph almost always looks like this. I'm not drawing that to scale. And there's typically a little elbow that happens, like a scree plot. Okay? And when you run an HCI experiments that's sort of sensitive to the response times, you need to make people practice first because they get better at things over time. So you can always, you might write a paper, you get reviews. Well, if people had practiced it, it would have been the opposite result. So generally speaking, you would do something like this. Have them practice. You plot their performance on those practice trials. And when they seem to get up to a high level of skill, then you run the experiment for exactly this reason. Okay, that's known as the power law of practice. Okay, and the last one I'll talk about is the motor system. This just translates thoughts into actions, mostly concerned about head, neck, arm, and hand, finger actions. That's pretty much what we do with the desktop. So the motor processor, it controls movements of the body. It's actually thought to have discrete micro movements that are sort of all uniform and equal. And those micro movements last about 70 milliseconds. Fortunately, that's less than the perceptual time of 100, so that our perception of ourselves and of each other seems to be continuous. But that's not quite accurate. And I'll show you some evidence of that in the next lecture on Fitts' law, where we actually think that it's a ballistic followed by a fine controlled movement, as opposed to discrete micro movements. And it chunks common behavioral acts. Okay. So I'm close to being done. I felt like I talked slow, but maybe I went faster than I thought that I did. But that's OK. We can fill the time with other things if people want to come ask me questions or about the lecture. So just in summary, the model human processor was a framework for understanding human information processing. It was, the impact was bringing cognitive psychology into UI design, which at the time was not what was happening. They were very different, very isolated, and that has stayed with us for a long time. It was also a catalyst for experimentation and modeling of human cognition. It's led to a lot of different types of UI design tools and a lot of different guidelines that we still put in practice today. And other things such as Gestalt laws still get used quite a bit today. OK, that is the end of my lecture. If there's questions, I'd be happy to respond as best as I could. If there's questions about groups, projects, enrollment, ask or come up in front and see me. I will see you next Tuesday, and have a nice long weekend. Yeah.